Okay. So I'm going to start with the midterm. First off, are there any questions? Just because we haven't had a class on Zoom, you all are free to unmute your mic, so you can unmute at any time. You can also like ask things in chat. I'll try and keep the chat up on my other screen so that if you can't unmute or don't want to unmute for whatever reason, that you can check in chat. So I don't see any questions. Okay, so I'll start by going over the midterm. Everyone's sort of curious about their marks, so let me show you the grade distribution, which is on Moodle. So I wasn't sure how this exam would go. It kind of went as expected. So this is the grade distribution. So it's out of 27. So you can see the highest mark was a 26 out of 27. So I think the exam was fair in that sense. Um, and then, but the average student was sort of in between sort of 10 and 17, sort of in this cluster here. Um, I'm not going to bell it because there's a high mark. Normally, I mean I can make it out of 26 instead of out of 27, but that isn't really going to do much. But what I do at the very end of at the end of the year is I sort of bell it. So don't worry so much strictly about like did I pass the midterm or did I fail? That's not really the important question. The main thing you want to do is try and figure out if you're kind of on the left side of this bell curve or on the right side of this bell curve. Okay, so if you're on the right side, kind of if you're here, you're doing very well in the course. If you're kind of on the right side, you're doing well, you're doing better than your classmates. And if you're down here, you might want to reflect on that and maybe try and study a bit more or come see me, ask me questions, that type of stuff. Okay. Um, so that's the distribution. All right. So everyone hopefully has a copy of their exam, or maybe you don't have it with you, but you have it somewhere. So I'll show you the right answers, and then you can compare it to what you have, and then you can kind of compute your grade, and you'll know which questions you got right and which questions you got wrong. I don't have the Scantron pieces of paper, so I can't. I mean, I could dig in and try and figure out which questions you got right or wrong, but it's too hard to do that for all students. So that's why I wanted you to keep the paper so that you could sort of figure it out for yourself. I do have the midterm marks, which I will try and put on Moodle. But anyways, you should be able to compute it yourself. Okay, so again, just interrupt me or drop a message in chat. You can just unmute and start talking. No offense taken if you do that, and if anything's unclear. Okay, so the first set of questions were true-false questions. So the first question says, Alice implements her favorite function as an arithmetic circuit. When she runs it 10 times with the same input, the circuit can use randomness to produce different outputs. So you'll recall that in class we talked about um, that circuits are deterministic. Okay, so deterministic means they cannot use randomness, so they don't have any randomness in it. So this statement is false. It's one of the sort of things that you cannot do with a arithmetic circuit. Okay, so for zero knowledge. Now there are ways to use randomness, but you can't do it in the circuit. Okay, so if you want to have randomness as part of your design, you have to have it as an input to the circuit. It can't be, you're not going to get randomness from the circuit itself. Okay, so if you run with the same input 10 times, you're always going to get the same output. Okay, that's what deterministic means. Okay, the next one says Alice claims to know a secret W such that Z equals f of x of W. So there's a function, there's two inputs, x and W, and she's saying that okay, this equals Z, and I know it's secret, so Bob doesn't know what W is. To check this claim, Bob must have a copy of each Z, F, X, W, otherwise he can't possibly verify it's true. And so the whole idea of a zero knowledge proof is that he doesn't need a copy of W. So there's a way of proving this is true without revealing what the value W is. Okay, so this statement is false. He does not need to have W in order to prove this. Okay, the next one says Alice posts a proof that her news photo is quote unquote real. Bob knows Alice has hacked her camera and copied all the keys inside of it. A ZK Snark can convince Bob that Alice's photo is real. So this was one of the examples we gave in class. The way that you prove it's real is you prove that it's signed by the camera. So the camera has a digital signature, and you prove that okay, this was signed by that digital signature. In this case, in this setup, because Alice has hacked the camera and has all the keys, she can generate signatures on things. Okay. And so ZK Snarks can't help you in this case. They're not going to bail you out. You can't really, ZK Snarks, they just prove that inputs to computations are right. Okay. So there are limits. They're very powerful. You can do a lot with them. But there are limits in terms of what they can prove. So a ZK Snark, there's no concept of what's real. What's real isn't, you can't capture that in a computation. The best you can do is say, well, it's signed, right? That's something that you can compute. You can determine whether something's signed or not. But if the signature is not working correct, then there's no guarantees. So this is false. A thing I'll also talk a bit about these questions themselves. So I don't know how you found the exam. You might find it a little bit maybe weird compared to other exams that you have. But this is the kind of thing that people ask you in real life, right? You get a job and people are like, okay, we, you know, Alice over here says that ZK Snarks can solve everything. And so we have this scenario, and can they actually solve it or not? And so a lot of times, like the knowledge that you need in order to do your job is more at a high level. It's not necessarily like I know the exact equations for KZG opening or something like that. These are things that you can look up and things like that. A lot of times, even in research, when you write papers and things, it's trying to find scenarios that fit the solution that you have. So you have a tool, which is a ZK Snark, and you're looking to see like, does it fit this scenario or not? So there'll be more questions, a whole page of questions along those lines as well. Okay, let me pause. Any questions so far? Again, just unmute or drop it in chat. Okay. All right, so the next ones get into more of the number theory stuff. So in ZP, the element 0 has a multiplicative inverse whenever P is prime. So that's false. So 0 does not have a multiplicative inverse. Everything multiplied by 0 is 0. So there's nothing that you can multiply by 0 that will give you a 1 instead. And so a lot of times we drop it from the group. And so we start talking about Z star P, which is basically all the elements of ZP without the 0. If G has order 11 mod 23, then G to the 12 equals G mod 23. Okay, so the way to see this is if G has order 11, then the exponent can be reduced mod 11. And so 12 mod 11 would equal 1. Okay, G to the power of 1 is obviously G. Okay, so this is a true statement. You can also see it from Fermat's last theorem if you want. Basically, you're just multiplying both sides by a G in order to derive this. Okay, question from the chat. So the marks are not on Moodle. So I wanted you to keep a copy of your question sheet with your answers marked so that you can go and you can follow along with this, and then you can figure out your mark for yourself. So you'll know what your mark is based on this. This I will post on Moodle. So I haven't posted this on Moodle yet, but at the end of this lecture, I'll upload this. So with your question sheet and with this answer guide, you should be able to figure out exactly which questions you got right and which questions you got wrong. The one thing that is on Moodle is just the histogram, because people are interested in sort of what the class average is and things like that. So you can see that. Okay, let's go to the next one. Alice picks an element G in subgroup GQ. It has size Q. She can reduce exponents mod Q. For example, A equals G to the A mod Q without changing the result. So we actually already, we just used this fact here, right? And so that's exactly correct. This is the property basically that you have when you work with things. When you know the order of G, then you can reduce the exponent by the order of G. Okay, so Q here. So in a little more generality, you could say it's always like A mod the order of G, and the order of G is Q, as stated. Okay, Alice sees that an element G has the following property. G to the Q equals 1 mod P. The order of G must be Q based on this alone. Okay, so if the only thing you test is this, can you conclude that the order of G must be Q? Okay, so this is maybe slightly trickier question. Uh, what this tells me is that it probably is order Q, but there's a chance that it's a smaller order. Okay, so it could be order Q, but it could also be, say, order 2 or order 1 even. Okay, so this is a necessary condition to check that the order is Q, but it's not sufficient. You also have to double check and make sure that it's not something of smaller order. Okay, now it didn't say safe prime here, so this explanation assumes a safe prime, but it's the same. If this is not a safe prime, it's also the same that there. In that case, you might have more smaller orders than just 2 or 1. So if it's a safe prime, the only smaller orders you'll have are 2 and 1. If it's unsafe, then you could have other ones as well. So it gets even worse. So you have to check even more things. You basically have to try and figure out all the things that you need to check. Okay. Um, all right. Okay, so question about the grades again. I have a spreadsheet with everyone's grades, so I can try to post it on Moodle. That's fine. That will not tell you which question you got right or wrong. It will just tell you what you got out of 27. Okay. If G is in GQ and H is also in GQ, then G plus H mod P must also be in GQ. Okay. So this is true if this was multiply instead. Okay. So GQ is closed under multiplication, but it's not closed under addition. So if you go adding two elements together, then there's no guarantee anymore that it's closed under multiplication. So you could bounce out of GQ. So this is false. Bob knows G to the X mod P, but he does not know X. He can compute G to the 5X mod P. So this is true. If he knows G to the X, all he does is he takes that value, whatever it is, and he raises it to the power 5, and then that will give G to the 5X. Even if G and H in a standard Peterson commitment, I didn't write commitment, but I think it's implied here. In a standard Peterson are chosen such that no one knows the discrete logarithm between them. Commitments are still not perfectly binding when used by an adversary with infinite computing power. Okay, so because with a Peterson commitment, there will be collisions. So there will be some other M and R pair such that these two equal each other. Okay. And that means it's not binding. So that means that in theory, you could open it up to M1 and M2. And so when we say it's unconditionally hiding, what we're actually saying is that it's not It's not binding. In order to be perfectly hiding, that means you can actually open a commitment up to every single message itself. The reason why this works in real life is because we don't assume anyone's walking around with infinite computing power. Okay. So normally you would have to solve the discrete logarithm between G and H in order to break binding. Okay. But if you have infinite computing power, you can compute the discrete log between G and H. Even if it's not given, okay, then you can just compute it directly, and then you can open it up to multiple messages. Okay. Okay, so a request to explain number six again. Okay, if G has order 11 mod 23, then G to the 12 equals G mod 23, right? So G to the 12 is equal to G to the 12 mod the order of G. Okay, so G equals 12 mod 11. Okay, and 12 mod 11, so that's one greater than 11. So 11 mod 11 is 0, so 12 mod 11 is 1. So this will equal G to the 1, which will equal G. Okay, 12. By mistake, Alice reuses the same randomness R in two Peterson commitments. So this R and this R are the same and sends them to Bob. Bob thinks M1 is twice as big as M2. Now he can confirm his guess. Okay, sorry, I wrote this down as false. It should actually be true. I think that was just a mistake. I'll double check and make sure that the marking guide that I use has this. Okay, so let's think about what you can do with this. So C1 divided by C2 would be G to the M1 divided by, sorry, I'll put in the H to the R, divided by G to the M2 HR. If you divide them, the HRs cancel. So that's the consequence of having it. And so you end up with G to the M1 minus M2. Okay. And M1 is twice as big as M2. So 2M2 minus M2 equals. Okay. Actually, I'm going to revert on this and say it's false. This actually is sort of, I did this question off the top of my head. I should have spent a little more time with it. So I wanted this to be true. I wanted to find a property where it was true. I kind of blew it because what you can tell a sort of additive relationship between the messages instead of a multiplicative one. So that's on me. It's not a great question to have asked, but the answer here is actually false. Okay. Uh, Alice and Bob hold 2-degree D polynomials and want to know if they're identical. Bob picks one coefficient to check at random. Alice confirms her polynomial has the same coefficient. Bob is correct in believing that they're very likely the same polynomial. So this is not true at all. So if you check two coefficients, it just tells you that that coefficient happens to be the same. It doesn't tell you anything about it. This sounds very, very, very similar to Schwartz-Zippel. That's the whole point of the question. But here, instead of checking one coefficient, what we're going to do is we're going to check one random point. Then it's true. Okay. Now, why is it true for a random point and not true for a coefficient? The point is that random points, there's a lot of them. So the Q is a large prime number, and so there's Q of them. Uh, the number of coefficients, there's not a lot of. Okay, the number of coefficients are just the size of the polynomial. So there'll be a coefficient for the degree of the polynomial. And so as a result, you're not going to get that like here the probability of getting away with cheating, you want it to be like a small number over a really big number, right? And so you're not going to have that really big number as the denominator of that fraction, which is your ability to cheat. So this doesn't work, but it does work if you pick a random point itself. Okay. Alice has two polynomials of degree 1000. When she adds them together, it's possible that the sum is a degree 43 polynomial. So this is true. What can happen is you can have higher order terms, like say you have x to the 1000, and let's say that this is a, and in the other polynomial, you have some coefficient b for that's along with this. If these two things add up to 0, okay, then they cancel each other out. Okay, so you can think of it as it didn't actually say, but it doesn't matter whether you interpret it this way or not. So in class, we always did things mod q. Okay, so a plus b would equal 0. This it doesn't specifically say mod q, but even if you assume it's not mod q, then you can think of a negative coefficient. So a plus negative a would give you 0. So in this case, they would cancel out. Now this order is gone, so that term isn't in the polynomial anymore. So the degree is one less. All right. So if all the higher order terms cancel each other out, it is totally possible that you can end up with a lower degree polynomial. Okay. You'll never end up with a greater degree polynomial, but you could, in theory, end up with a smaller one. But it would specifically have to be the case that that all the coefficients would cancel out. Canceling out means that when you add them, they sum to 0. Okay. The next set of questions deal with um, just sort of identifying when a snark is appropriate or not appropriate. So there's four options. You can just do a basic snark without the zero knowledge component. So all the inputs are known, but it helps to do a snark. You'd rather verify a proof than see, which is directly compute the result. Okay. You might have to use a snark because one of the witnesses is secret. Okay. So as soon as you have like a secret with a secret input, then you are going to be in the ZK snark world. Okay. If these are no secret inputs, then you're here. And C would be good for simple things. So first off, you need no secret and you need something that's simple. Okay. There's no like hard rule for like where's the line drawn between where it becomes simple or not. So what I did is I tried to pick things that were just so simple that it was obvious that a snark isn't going to help you. But this is the kind of thing, again, if you say you get a job and people are like, okay, we want to use snarks, you have to say, okay, that is a use case for snarks, or that doesn't work. Snarks don't help you, or they do work in theory, but you could also just directly recompute the result. Okay, so there'll be a couple of cases where ZK snarks just don't happen. They don't help at all. So we'll see those when we go through. Okay, so the first one says Alice wants to prove to Bob her tax software computed her refund correctly. So that's the output of the function from her private input and deductions. Okay, but she does not want to reveal the underlying amounts. Okay, so this is clearly a case where we have secret inputs. So this is going to be B. Alice sends to Bob a 2-page PDF document, and Bob wants to check that the first page of the file displays correctly. Okay, displays correctly. That you can just, I mean, the only way to know whether it displays correctly is to just open it and look at it. Okay, So in this case, you're going to see, you're not going to use any zero knowledge. You're just going to open the PDF and make sure it looks okay. Alice has a grade sheet on Moodle served over HTTPS, so it's private. She wants to prove to the class that the exam average is 80%, but not reveal any individual marks. Okay, so it's secret input. So I'm showing you the class average, but I'm not showing you every individual's mark. In this case, I need the ZK part, and so it's going to be B. Alice claims a number U is the modular inverse of V mod P. Bob wants to check. So in this case, Bob knows U and Bob knows V and he knows mod P. He can check it himself. And so it's just easiest to just directly check it with C. Okay. You could prove this with a snark, but you're not going to do, I mean, it's just one multiplication to check it. A snark is obviously going to be a lot more than a multiplication. You might have to commit to things, and right away you've already spent more than a computation. Or sorry, than a multiplication. Alice and Bob have a private salary number, and they want to learn earns more or whether they're equal without revealing the actual salaries. Okay. This is something that sounds very close to what a ZK snark would provide. Okay. We have a secret input, which is a salary, and we want to learn a fact about it. But the subtle difference here is that we have two secret inputs. So Alice has her secret input, and Bob has his secret input. Okay. In a zero knowledge system, we assume that whoever's proving it, the prover, they know all the inputs. So Alice can't prove this because Alice doesn't know Bob's secret input, and Bob can't issue a proof for this because he doesn't know Alice's secret input. Okay, so this is actually not possible. You can't use one of these technologies to do this. What you could do instead is something called, we don't cover it in this course, but there's a different uh, cryptographic technique called multi-party computation that would let you solve these kinds of problems. Okay. So sometimes when you're looking at applications in the real world, it looks like something that a ZK snark could help with. And you think, okay, yeah, that looks like a snark. But you realize once you sit down and think about it, you think, okay, well, actually, it's more of a multi-party computation than a ZK snark. So that's a very common thing that happens. Okay. The next one says Alice wants to prove the Fear of God luxury hoodie. So this is just a brand of luxury hoodie is selling on eBay to Bob are authentic originals and not fakes or replicas. So in this case, there's no computation. This isn't a question that can be answered with computation, right? You don't know whether it's real or not. You'd have to like look at the sweater and examine the stitching or things like that. And even then, at the very end of the day, you might actually not know whether it's legitimate or not. Maybe it came from the factory that created it, but it just wasn't part of the production run of it itself. Okay. So snarks are only going to help you with computations. Verifying inputs to computations give you the right output. So this will be none of the above. The last one says Alice trains a public machine learning algorithm on a large set of Bob's files. So I'm going to assume that Bob knows his own files. They're his. Okay. So Bob wants to verify the training was done. Because it's a large set, okay, that's sort of the key. We're in this world of between A and C. Is it a simple thing that I'm verifying, or is it a large thing? So there's no secrets. So I can do A or C. And because it's a large set of files and machine learning algorithms are complicated, I much rather verify a proof than directly redo it. Okay. So this would be in the world of A. Okay. Question. Okay, so I think the question for 20, okay, yeah. So if there's some sort of if there were like digital signatures on a hoodie, then you could imagine something that would do a computation. So what would have to happen is let's say there was a tag and then it was digitally signed by the company that produces it. Then what you could do is you could try and prove that um, that the signature is correct. Now, if you want to go down that route, the correct answer there would be C, not A, because verifying a signature is cheap. So you would just verify that it's correct. However, that doesn't work because anybody can, if you get one legitimate hoodie, right, you can take a picture of what the QR code is, and then you can print out that tag and you can attach it to the fake or the replicas. Okay. So one thing about a digital signature is it has to it has to attach itself to the message, right? But here you have a signature. It's just sort of you have the hoodie and you have the signature. They're floating side by side. Okay. But that signature isn't really attached to that sweater, other than like the fact that maybe it's physically attached. Okay. But if the sweater were to change, the thing that was attached would not change. Okay. In a digital signature, let's say I have a message and it's signed. If I change the message itself, the signature no longer is valid. Okay. Here I could completely change the sweater, right? I could replace it with a different sweater and keep that same tag, and it's not like the tag breaks as a result, right? It's still a legitimate tag itself. So QR code tags and things like that. It's a good idea, but it's just not going to work in this case. Okay, we'll go to the next ones. Okay, so the elevator in the EV building has 15 floors above the ground floor. Assume five people enter the elevator at the ground floor. What is the probability that at least two people get off on the same floor? Okay, so we're talking about 2 out of 5 get off, and there's 15 floors. So you have five people, 15 floors. So five people are basically going to 15 floors. So we have 15 floors. So the first person will get off at, say, a random floor. Second person will get off on a random floor. Third person will get off on a random floor. What's the probability that there's a collision, that two people are going to select the same random floor in order to get off? Okay. This is an example of the birthday paradox that we talked about. And the exact math here doesn't matter. So I tried to set this up so that you don't have to compute 53%. It doesn't matter whether it's 53%. What I wanted you to do is recognize that it has to be bigger than 33%. Okay. 33% is the probability that, what's the probability that one of these five people is getting off on the same floor as you? Okay. Then it's going to be, well, 5 out of 15, which is 33%. Okay. So that's the probability. But when you say anyone can get off on the same floor as anyone else, right? Then this person has a chance to get off on the same floor as this person or this person, right? When we add five people to the scenario, I have a 33% chance of getting off with this person, but I also have a 33% chance of getting off with this person, and a 33% of this person, and a 33% of this person. So the probability that I'm going to get off on the same floor as one other person is got to be a lot higher than 33%. Okay. So 53% is, if you want to calculate it out, it is. But again, I set it up so that basically I just want you to recognize that this is a birthday paradox. The probability is a lot higher than you would expect. What you would expect is this, but because of what makes it a paradox is that it's higher than this probability, and this is the only number that sort of makes sense ballpark. Okay. Bob gives Alice Peterson commitment to, and then opens a commitment to two different messages. Okay. He then gives Alice a Feldman commitment to a third message using the same generator G as he used in the Peterson commitment. Which of the following statements must be true? So we have G to the M1, H to the R1. We have G to the M2, H to the R2. These two things are equal. Okay, so they open up to the same value. And then we have a third message, which looks like this, G to the M3. Okay, so these are all the facts that I know. Okay, now because these two things are equal, The other fact that I can derive is I can figure out what the discrete log is between G and H, which I'll write as this way. But knowing the discrete log between G and H, it doesn't actually help me much with a Feldman commitment because there's no H left at all. Okay. So let's just go through the options one by one and see why this one's true and the other ones aren't. So Alice can use the two openings to break the discrete log problem. So that is true. They can do it. But can you do that to break the hiding property of the Feldman commitment? Well, you don't need a discrete log between G and Y, or sorry, H and G. You need a discrete log between G and whatever this commitment value is. I called it Y. Maybe C is a better word for it. Okay. So you need, it's close. You're getting the discrete log of something, but it's not the right discrete log. So you need the discrete log between C and G. Okay. So this was the answer that was sort of the spurious answer. It's the one that looks like it might be right, but then hopefully when you think about it a little deeper, you realize that it's not the right answer. Okay. Um, Feldman commitment's binding property is broken, so that's not true. So there's only one M3 that will produce G to the M3, so it can't possibly be that. The Feldman commitment is unconditionally hiding, so that's not true anyway. No Feldman commitment is. Peterson commitments are, but Feldman commitments are not. The Feldman commitment is hiding, so that's true. It's true that you can't extract M3 without breaking the discrete log between G and C. Okay. If you have a guess at what M3 is, you could very well guess. Okay. And it's binding. It's perfectly binding. Okay. So there's only one M3 that you can possibly open this to. Okay. So it's hiding as long as you can't guess the value. So that is true. And it's also binding. So that's also true. And so this D is true itself. Okay. Alice has implemented her favorite Boolean function using only NAND gates. Now she's also allowed to use other Boolean gates and or not an XOR and an addition gate as well that outputs the arithmetic addition of a left gate, a right input, a left input, right input mod Q on two elements from ZQ. Okay, so what statement is the most accurate? Alice can now generate zero knowledge proofs that hide some inputs. So she could do that before, even if she only had NAND gates. She could do it before and after. So that's not true. She can implement more complex functions. So this is what you would think would be true. But what we showed is that with a NAND gate, it's a universal gate. What that means is that you can implement any circuit that can be implemented with only NAND gates. Okay. It might be a bigger, more complicated circuit because you are only using one type of gate. Okay. But you can implement it. Okay. So that's not true. Alice can likely implement her function using less gates. So this is true. So that's basically what extra gates give you is let's say you're doing an AND somewhere in your circuit. Instead of having to implement the AND with say 2 or 3 NAND gates, you can just implement it directly with one NAND gate. Okay. So every gate that you have in addition could make your circuit smaller. It could require less and less gates. But every function that you can implement in one of the two worlds. Okay. So extra gates give you efficiency, but they don't unlock being able to implement other kinds of functions that you weren't able to before. Size of the circuit goes from linear to constant size. So this is false. You probably will still need you'll still need a linear number of gates. This is meant to sort of sound like a snark where we have this succinct property, but the succinct property doesn't apply to the circuit. It applies to the proof that the circuit is correct. Okay, Alice has D plus 1 unique points sampled from a degree D polynomial P. Which of the following statements is the most accurate? Okay, can she efficiently find its D plus roots? So that's not, you can't efficiently find roots, as we stated in class. Alice can add it by another degree D polynomial without interpolating if she knows the evaluation of the second polynomial at the same coordinates. So this is true. So what that means is if I have a polynomial and I know, say, these 3 values on the polynomial, and then I have a second polynomial, and I know the same three values on this polynomial, okay, then I can simply add these points together, and that will give me the new polynomial. Okay, so that's the sum of the two polynomials. And I just know it at those 3 points. But then I can, if I need to get coefficients, I can interpolate it. But I have enough information I fully have specified what this blue polynomial is. Okay, so I don't have to go back to coefficients and then come back. I can just add them directly. By Schwartz-Zippel, Alice can choose one random point and use it to interpolate and determine the coefficients of the polynomial. So you cannot do that. If you're interpolating, uh, you need d plus one points. If the domain is FFT friendly for roots of unity, then Alice needs d log d points to interpolate. Again, so the d log d corresponds to how much work it is to interpolate. It's how much work you have to do. It's not the number of points that you need. Okay. You're always going to need d plus one points for a polynomial that's degree d. So these answers don't really make logical sense. They're just, I just sort of threw some stuff that if you kind of know the terminology, maybe you think that these are the right answers, but don't read too much into these answers. It's just sort of throwing together like some terminology that we used in the course to make it maybe sound like it's possibly a right answer. Okay, let's see equals g to the p of tau be a KZG commitment to polynomial p. Alice claims that she can open this polynomial at the point z, and it will give the answer y. And she has a proof of this statement. Which statement is the most accurate about what pi represents? Okay, so what is the actual proof it is? Okay, and so the proof is going to be a commitment to q, where q is the polynomial, you slide it down by y, so now it's a root. And because it's a root, x minus z will evenly divide that polynomial. Okay, so the divisibility of this by x minus z will enforce the fact that p of z equals y. Okay, I viewed this as like sort of an easy question. It looks maybe complicated because of all the math, but this is like the direct definition of KZG if you go to the notes. Okay. These other ones don't work, and they just kind of they don't really make logical sense. I had to write down some answers that maybe possibly looked right, but we can try and go through them. So pi is g to the pz. So in that case, you actually already have that value. So you have a commitment, which is effectively that as well. And from here, if you get it evaluated at z instead of evaluated at tau, you're not able to figure out whether that's a right value or a wrong value. G to the tau minus y, they check this equals 0. So it doesn't make sense. You can work out what this check does, but it doesn't do anything at all. G to the z x minus z, so that's the denominator. And then the pairing check works because this is 0 at x equals 0. Okay, so again, the proof here, you can notice it has nothing to do with p. I don't even use p anywhere in the proof. So it can't possibly, this would be true, period, for any polynomial. It's not even functionally dependent on the polynomial at all. So there's no possible way that this could do anything useful at all. Okay, 27. The structure reference string contains elements like g to the powers of tau, we call it. What is the most accurate reason KZG can commit to a degree d polynomial? Okay, so it's because you can form the polynomial of tau using these powers and exponentiation. So you can basically you can take this, you can multiply in your coefficients and multiply them together, and you'll get g to the p tau. Again, this is basically just the straight out of the notes how we do it. And then these three are just kind of, again, they're kind of gibberish answers that just try and use some terminology to sound like maybe they are right. Tau is public and everyone can compute this. So this is true if tau were public, but it's not. So that's the basic idea of KZG is that tau is a secret that nobody knows. Because FFT is used to evaluate P at roots of unity. So this just, it has not, I don't know what to say about it other than it has nothing to do with anything. Because Schwarzschild guarantees correctness, so that also doesn't help with anything. Um, okay, so that's the last question. All right, now I'll just pause and take any questions that you might have, either in chat or you can just unmute and ask. Okay, all right, so seeing none, let's switch over to what we talked about last class. Okay, so last class we oh sorry, there's 1 and 3. Sure. Okay, so there's a request to look at 1 and 3 again. Alice implements her favorite function as an arithmetic circuit. When she runs it 10 times with the same input, could it give you 10 different outputs? It cannot. Circuits are deterministic. Okay, so circuits, same input always gives you the same output. So if you run it with 10 times with the same input, you'll always get the same output. And this one, again, it ties back to you, if you want to prove something, it needs to be based on computation. So it can't look at a photo and know whether it's real or not. It needs to have computation. Okay, so another follow-up question is, what about using randomness? So I'm not sure what you mean by that exactly. Basically, if you want to use randomness can come into play in one of two places. So you have a circuit. Either the circuit is using randomness, so like the gates are random. So like sometimes one XOR one is 0, and sometimes that one XOR one is not 1. So that's what it means for a circuit to be random. Or you can have randomness in the inputs itself. Okay. If you want to have randomness in the inputs, that's fine. You won't have the same input though. So if you have the same input, that means you have the same randomness. If the randomness is the input, then you're running that circuit if you're running the circuit 10 times with the same input, you're running it 10 times with the same randomness. And so you're always going to get the same output. Yeah, if you run it with 10 different inputs, then you could get 10 different outputs for sure. Yeah, so if the inputs are different, then the outputs can be different. But if the inputs are the same, the outputs have to be the same. That's what deterministic means. Okay, and then for 3, so yeah, so like let me just give an example. All right, so if X is always the same, Y is always going to be the same. That's pretty obvious, right? Um, The alternative world would be that well, there's two alternatives. One is that somehow the function is random. So every time I run X, the gates, sometimes they output one thing and sometimes they output another thing. So I can get different Ys. So that's not happening here. So F is deterministic. Okay. It's possible in real life. Like if you want to have a computer that has noisy gates that do it, like there's not like I'm not saying it's physically impossible. It's just that the assumption that we're using when we do ZK SNARKs is that we're only modeling deterministic functions. Okay. The second kind of thing you can do is something like this. Okay. And so if R and X are the same, Y will be the same. They have to be because F itself isn't, you're not getting any randomness out of F itself. So if X and R are the same, if they're fixed, then Y is also fixed. Okay. If you start varying R, so if you keep X the same and you're choosing this at random, then you are getting different Y values. Okay, so you'll get different Y values. But in this case, your input is not fixed. The reason you're getting different outputs is because you have different inputs itself. Okay, so you can have random functions and you can model them with SNARKs, but the way that you do it is you put the randomness as an input to the function. It's the only way that you can model it.
So in question, it's mentioned that we have same input. So randomness is same in every input, something like that.
Yeah, so same input would be that the X value and the R value are the same, so they don't change itself.
So where are we using randomness for like in function or in?
Yeah, so what you can do is I can say I'm choosing this R at random. So the prover or the person running the circuit can choose R at random itself. So if you want to use randomness, you can say I'm about to compute the function, and so I'm just going to pick a random number, and the second input to the function will be whatever random number I draw. And then tomorrow, if I run the same function on the same X, I'll pick a different random number and then I'll run it and I'll get a different Y because well, presumably because I chose a different random number here.
So does
Yeah.
the question not state that we are using different random numbers, so it should give different output? That's what I understood.
Yeah, so it was meant to say the circuit can use randomness. Okay, so the circuit, randomness in the circuit itself. And it also specified that the inputs are the same.
Okay, got
So I
it.
think the question stated fine. But yeah.
Okay, got it.
Okay, and then do you want to ask your question about three,
Oh, I just
or is
missed
it
the
clear?
explanation. So if you
Oh,
could
okay.
repeat.
So the basic idea here is that um, whether a photo is real or not isn't a computation. It's not something I can compute, so I can't use a SNARK. But what we said in class is, well, if the camera is digitally signing images, then what you could do is you could prove that it is an image that was digitally signed by the camera. And that's like close to being real, right? I noted there's a few exceptions, like you could use the camera to take a picture of a fake picture in order to make it. But anyways, but here because the camera was hacked and all the keys are broken, the digital signature isn't working anymore. Okay, so I have nothing left to prove. I can't prove that it's real anymore because it relies on the fact that those signatures are working correctly. Okay, so this question is meant to model that ZK snarks can't solve every problem in the world. They can only solve problems where it's a question of a computation and whether certain inputs are producing a certain output.
Right.
Okay, good. Okay. The second thing is that some people were confused by polynomial commitments. And so I maybe didn't explain it as well as I could. So what I thought I would do is I just sort of go over the lecture notes again, and we'll just kind of talk about them. I won't write out so much, so you can just sort of follow along. I'll use it almost like slides and just sort of point at things to explain it. Okay. So a polynomial commitment, what we're doing is we have a polynomial. Okay. We don't know what form it's in yet, but since you've already seen KZG, the form that we need the polynomial in is we need a list of its coefficients. Okay. So if we don't have its coefficients, say we just have some points on the polynomial or we have the roots of the polynomial, we'll have to first convert it into coefficients. But that's fine. We can use interpolation to do that or multiplication. And so now that we have the polynomial in coefficient form, I want a function that I'm going to be able to commit to this polynomial. Okay, so I'm going to produce a C value, and I'm going to look for three properties. The first thing is if I commit to this polynomial, I shouldn't be able to later say, oh, I actually committed to a completely different polynomial. Okay, so the I actually committed to this polynomial, poly, and later I don't want to reveal that this was my polynomial. I want to change it. So I'm changing it to poly prime, which is a different polynomial. And somehow I'm able to convince you that actually C is a commitment to this polynomial, not to this polynomial. Okay, so that should not be possible to do. So we call that the binding property. The hiding property is that if I give you C, can you figure out what polynomial is? Okay. And the answer is that you can, so for KZG commitments, you can actually run it in one of two modes. You can run it in a mode where it's not possible to learn what the polynomial is by looking at C. And there is another mode where you might be able to guess if you have a guess at what the polynomial is, then you can test whether your guess is correct or not. Okay. The mode is now, so there's a hiding and a not hiding version of it, or kind of the term they use is a sort of Feldman style or a Pedersen style version of these commitments. Okay. Now, how do you choose which one you want to use? Well, the one where it is not hiding, the one that's hiding is strictly better from security perspective. So you might say, let's just always use the hiding polynomial, because even if we don't need it, why not have it anyways? And so the answer is just that it comes with a penalty in terms of computation. So it's a little more expensive to create a commitment, and then opening things up and things like that will be a little bit more expensive. Okay. So the reason that you might not want to use the KZG that's hiding is just that it's cheaper. Also, for this course, it's easier to understand. So the math is a little bit easier to see if you consider the one that's not hiding. Okay. So in other words, KZG, there's two modes. One mode is hiding, one mode is not hiding. And if you're doing SNARKs, you don't need hiding anyways. So you might as well use the easier, simpler, more efficient version. And if you're doing ZK SNARKs, then you absolutely need hiding. So you have to be using the KZG, the hiding version of KZG. Okay. Now, in software, when you implement these things, uh, you know, you just sort of you tell the code which version you want, and then it figures it out. Okay. So it's like pretty simple to switch from one to the other. Uh, and so in this class, what I'm going to do is I'm just going to show you the first one, the non-hiding version. I give you a hint at what we would do to make it hiding if we wanted to. So we have this polynomial, and when we commit to it, we have g to the p tau. So this is, if we just stop here, the g to the p tau, this is the not hiding version. Okay, so this is the KZG commitment that's not hiding. To make it hiding, to add the hiding property, we have to add an h to the r onto the end. Okay, and then that makes it hiding. And it turns out that that's not quite sufficient. There's a few other little things there's one other little thing that we have to do, but that gives us the sort of hiding variant. Okay, but I'm just not considering this because it's more complicated to explain. It's already complicated enough. Let's do ourselves a favor and not consider the hiding version. But later, if you need the hiding version, you can learn how it works. And if you're doing software or something like that, then you can also just have the software figure it out for you. Okay. The last thing we want is we want the commitment to be succinct. So what I want is I want C to be short. And in particular, I want it to be short regardless of how big the polynomial is. So even if the polynomial is 10,000 or 10 million coefficients long, it would take megabytes or uh, maybe gigabytes, probably not, but it might take megabytes just to write down how big the polynomial is. I want a short commitment to it. I would just want a couple bytes that describe what the polynomial is. Okay, so we call that succinct. So the size of the commitment is quote unquote small. There's different definitions of what small needs to be in order to qualify as being succinct. But to keep it very simple in this class, we'll think of it as constant size. So in KZG, the commitment that you get out is always the same size. It doesn't matter if the polynomial is degree 10 or if it's a degree 10 million, it will always give you the same size C. And it will continue to be hiding and binding as well. Okay. Then what do we want to do? So once we have a commitment, we want to do things with it. So the first thing is we want to be able to create the commitment. So I have a polynomial, I feed it to a commit function, it produces the commitment for me. I might want to open up the polynomial and reveal that the polynomial that I committed to in this commitment C is this polynomial. Okay, so that's true. And the way that you reveal it is you just reveal the polynomial, you reveal C, and then the verifier just they commit to the polynomial revealed, and they try and make sure that it matches the same C that you gave them before. Okay. We won't do this in this class, so we're never going to open up the whole polynomial, but it is something that you can do. The thing that we'll do that's sort of the fancier version of a reveal is what I want to do is I want to open the polynomial only at a specific point. So I want to prove that I'm not going to tell you anything about the polynomial other than if you evaluate the polynomial at the value x, you will get the value y. So p of x equals y. That's the fact that I want to reveal to you. Okay. And you won't learn anything else about the polynomial. Okay. So you won't know any of its coefficients. You won't know how it opens up at other points other than x. You're only going to know that this one point, it opens up at this one point. Okay. And this is going to be very useful for SNARKs itself. Okay. So what we want is now another thing you might think is if you know about what a hash function is, you might say, well, why don't I just hash the polynomial? So we can go through this and see why that works or doesn't work. So if I hash the polynomial, it's binding. If I hash the polynomial, it's hiding. If I hash the polynomial, it's succinct. If I hash the polynomial, I can commit to the polynomial. I just have to hash it. If I hash the polynomial, I can reveal it, and then someone can take what I reveal and hash it and make sure that it matches what I was saying that I was committed to. But where it breaks down is the selective reveal. Okay, all I can do is I can open up the hash and show you the full input to the hash. I'm not going to be able to open it up to just one specific value itself. Okay, so the whole reason that we're doing KZG and we have all this fancy math and things like that is basically to try and realize this property. This is the tough property to realize. Okay, so that's the sort of setup of what a polynomial commitment is. Are there any questions on that so far? Okay. Um, there's a question, should we take a break? We can, yeah, we can take one now. So why don't we do that? So why don't we come back at 1 and pick it up from there. Okay, first off, any questions so far? Okay, so the next thing we talked about is this sort of idea of homomorphic operations. And so I noted that if we just go back to Feldman commitments for a second before we talk about polynomial commitments, but this will be true of polynomial commitments as well. If you have the commitment to A and a commitment to B, you can compute a commitment to A plus B, even though, and anyone can do this. Okay. So the person who knows A that makes the commitment to A and the person who knows B can obviously commit to A plus B. Okay. But the point is that if you give me your commitments to A and B, I have no idea what A and B is, right? I can compute the commitment to A plus B. Or if you want to think of it slightly different, I can check whether this third commitment is actually a commitment to A plus B simply by multiplying these two together. Okay, so what I can do is I can sort of do an addition under commitment. Um, then we talked about could you do a multiplication under commitment? And the answer is you can't do it as cleanly as you can do with an addition. So if I have a commitment to A and a commitment to B, I can't just compute a commitment to A times B. If I could, that would unlock something called fully homomorphic. Usually it's associated with encryption, but you could think of it in terms of commitments. And that kind of thing is possible, but those schemes are very inefficient. And in this class, we're focusing on things that are very efficient. Um, And so you could in theory do it, but with these simple, efficient styles of commitments, no one knows. I'm not saying it's impossible, but at least nobody knows how to compute that. Okay. But what we can do is we can get close with this operation called a bilinear pairing. And we spent a bunch of time on it. It's sort of complicated. And at the end of the day, honestly, it doesn't really matter all of the details. Um, the only detail that really matters is that you can check if I give you a commitment to A and a commitment to B, and I assert that this is a commitment to A times B, okay, you can check whether that's true or not. You can check whether this is actually a commitment to A times B. Okay. But I have to give you, you can't compute it for yourself. So that's what's the difference with addition. With addition, even if I don't tell you what A plus B is, you can compute it yourself. Okay. Here I will tell you what A times B is, and then you can check that multiplication was done correctly. Okay. And the way that you check it is you use this pairing. And anyways, you'll see like the one time that we use it is when we do this opening proof, and you'll see exactly how it's structured. And you don't have to understand all the ins and outs of pairings. You basically just have to understand why they let you check the one multiplication that you need in KZG openings. Okay. So I'm just going to sort of gloss over that. And now I'm going to turn to the polynomial commitment scheme. But before we do, is there any other questions? Especially people found stuff unclear. And so I'm not sure exactly if it was once we got to KZG or if it was the stuff before it. But if there's things that aren't clear to you, now's the time to ask. Okay. So what we're going to do is we're going to have a way of committing to a polynomial. Okay. And so what I'm going to do is I'm going to take the polynomial I want to commit to. I'm going to put it in coefficient form. So I have these coefficients. And in a polynomial, there's the variable, right? So there's an x value. And every time I change the x value, I get a different y value. Okay. So where the variable goes, I'm denoting by the box. So the box is where the variable goes. And that can be anything. It could be a 3, a 5, a 7. And every time when I evaluate this, I will get a different answer. Okay. Maybe I get the same answer, but I have the potential to get a different answer for every value that I put in. Okay. And so when I commit to a polynomial, I want to commit to the coefficients, but I don't, because the box is a variable, I don't know what value to stick there. Okay. So the first insight of KZG, there's maybe like two or three like kind of key insights to KZG. The first insight is if you stick a random value here, nobody knows it, all right, then it's as good as you committing to the whole polynomial. Okay. Why is that the case? Well, let's say I want to break the binding property and I want to open this commitment. I commit to polynomial A and I want to open that commitment to polynomial B. Okay. The only way that they'll produce the same commitment is if they produce the same value at tau. So in other words, I have a polynomial that I actually committed to, and I have some other polynomial, and I want to lie and say, after I committed to A, I want to lie and say, actually, what I committed to was B. Okay. I can do that. I can lie and get away with it if and only if the values at tau are the same. So if the polynomial at B happens to have the same value, if there's an intersection between the two polynomials at tau, then I can lie and get away with it. Otherwise, I'm not going to be able to lie and get away with it. Okay. All right. If I know what tau is, that's easy. I can create a polynomial and then I can make sure that it has the same value as A at the value of tau. But if tau is a secret, nobody knows it, then I have to guess where tau is, right? I have no idea where tau is, so I would have to guess. I can make a polynomial B that intersects with polynomial A at a certain number of points. Okay, so I can say, okay, I want my B to intersect at a whole bunch of points with A. And if tau happens to be at one of these points, then I can get away with lying about it. But if it doesn't, if tau is somewhere different, then the polynomial is going to be different. Okay. So then the question is, well, how many points can I, if I want B to be the close to A, I want it to overlap or intersect at as many points as possible. How many possible points can I have it intersect with A? And that's bound by the degree of the polynomial. So assuming that A and B are both degree D, then I can have it intersect at most D points. All right. And what's the probability that tau will be at one of those D points? Well, it's going to be D over the number of values of tau, which is huge, which is Q. Okay. So the probability that I can break the binding property of this polynomial is going to be D over Q. All right. And so remember, Q is a big, you know, a, a prime number that's like 256 bits. Okay. So this just it's not going to work at all. Okay. And so this is the Schwarzschild lemma that basically says that if you look at a random point and the two polynomials are the same at that random point, with very, very high overwhelming probability, they're the same polynomial. Okay. So if you want to talk about a polynomial, you don't actually have to talk about the entire polynomial. You can cheat and just talk about what that polynomial's value is at a random point. And that's as good as like thinking about what the actual polynomial is at all points. All right. So that's what KZG does. It doesn't try to commit to the polynomial at all possible values. It just commits to it at one particular value, but it's specifically set up so that no one knows it. All right. Then the next question is, well, how on earth are you going to, I mean, I have to compute this value. Like I have to fill in a value for G. I have to put in a number for C0, for C1, for tau, for C2, for tau squared, for CQ, for tau cubed. I have to put actual numbers in for all of those things. How am I going to put the numbers in if I don't know what the value of tau is? Okay. I know what the values of C's are. They're my coefficients. That defines the polynomial that I'm committing to. I know the value of G and P and all of these things. They're just the sort of the crypto parameters of the system, but I don't know what tau is. Okay. So what we said is, well, there's this magic protocol that's going to give you concrete numbers for G, G to the tau, G to the tau squared, G to the tau cubed, G to the tau 4, all the way up to certain, it might be to 10,000 or something like that. Um, and this is going to be published, say, online, and anyone can use these strings. And for something that's very closely related to the discrete logarithm problem, if I know the number here, like say this equals 15 and this equals 17, I would have to break the discrete log problem to get tau out. So just seeing these values doesn't tell me what tau is. So it's safe to publish these values. Uh, and if I publish them, then what I can do is I can take these values, I can exponentiate my coefficients in, and I can end up with C0 plus C1 tau plus C2 tau, even though I don't know what tau is. Okay. And the reason I'm able to do that is because of these homomorphic properties. So that if I have a commitment to A and I raise it to the power of B, I get a commitment to A times B. Okay. So I have a commitment to A. That's, you can think of this as a commitment to tau, and I'm exponentiating in C1, so I'm getting tau times C1 here. Okay. Then there's the question of, well, where does this come from? If nobody knows tau, where does it come from? And so the answer is, well, people compute it. They do know tau for a second while their computer creates this string, but then they delete tau right away. And then someone else does it with a different value of tau, and someone else does it with a different value of tau. And then there's a way to combine all of those together so that that everybody would have to reveal what value they were using in order for someone to know what tau is completely. Okay, so this we call it a trusted setup, but it's also universal in the sense that once you do this once, then everybody can use it. So for KZG, you can everyone can use the same setup. So just one person has to do it once, and then all of us can use it, and now we're set, and we can keep using it for 10 years or whatever. So we don't have to redo this every time we want to do a commitment. It's just a one-time setup cost that you do at the very start of the protocol itself. Okay, so this is how we get the commitment to the polynomial. So we said there's a bunch of operations that we want to do. And so up to this point, we've only done the first thing. We haven't looked at revealing at all. I've only shown how to commit to the polynomial itself. So I have the polynomial as a set of coefficients. I use the trusted setup, and I'm able to produce this value C itself. Okay, questions on this so far? Okay. Then let's talk about the sort of harder part, which is I want to open the commitment at a certain point. Okay. So I have a commitment. It looks like this. It's g to the c0 plus c1 tau plus c2 tau squared plus blah, 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 blah. Okay. So in other words, it's the coefficients again. They're the values that I know. They define the polynomial. The tau is the secret. I'm able to get this value constructed without learning what tau is because I have powers of tau. And so what I effectively have is g to the power of my polynomial evaluated at tau. Okay, so that's the y value of it that's sitting there. Now what I want to do is I want to prove that for my polynomial, it has a root at the value x. Um, I don't have a picture, so let me draw it. All right. So I have this polynomial p. All right. And at this value here, x, it crosses the intersect here. So y equals 0 at this value. Okay. So x0 is a point that's on this polynomial. It exists along this polynomial. Okay. So I don't give you the polynomial itself. I just give you a commitment to the polynomial. Okay. And what's the commitment to the polynomial? Well, it's basically just the value at tau. So let's say that tau happens to be here. No one knows where tau is. Let's say tau happens to be here. So basically, this is what I give you. I give you p at tau. Well, I give you g to the power of p at tau. And now I want to prove to you that x and 0 is a point that's on that commitment, that's inside the commitment to the polynomial, that's on the polynomial that's inside the commitment that I gave to you. Okay, so how am I going to do this? All right. Um, so there's this property that we have, which is that polynomials, if you know the roots of polynomials, then what you can do is you can put your polynomial into this form where it's the variable minus the root, the variable minus the root, the variable minus the root, all multiplied together. Okay, so that's what the roots look like. So what I'm going to do is if I claim that x is a root of this polynomial, then what I should be able to do is I should be able to divide my polynomial by variable minus x, and this should cancel out with one of the roots. Okay, if x is a root, then if I were to factor this polynomial by all its roots, then this root will be sitting here somewhere. Okay, so somewhere up here, this root will be sitting here, and when I divide by this, it will cancel out, and I'll just be left with a polynomial with all the rest of the roots itself. So that root will divide off of it. Okay. Now let's say that this is not a root of the polynomial. Okay. Then this will not cancel. Okay. So what will happen is it won't evenly divide. And so what I'll be left with is I'll be left with an expression where I have some stuff on the top of the expression and I still have some stuff on the bottom of the expression as well. Okay. And so if I have stuff on the bottom of the expression, it's no longer a polynomial. Okay, so I can do the division, I can do it in a sense, and I will get an answer, but the answer will not be a polynomial. Okay, the answer is going to be, we call it a rational function because it has stuff on the top and it has stuff on the bottom. It doesn't fit the pattern of a polynomial. Okay. And because it doesn't fit the pattern of a polynomial, I'm not going to be able to commit to it using KZG because KZG is for committing to polynomials, and it's not going to behave like a polynomial. Even if I could somehow squeeze it into a commitment to something, it's not going to have the same properties of a polynomial. So like multiplication and division and things like that aren't going to work correctly. Okay. So what I'm going to do to prove to you that this is a root is I'm going to say, take the commitment to the polynomial, divide it by a commitment to this polynomial. Okay, notice this is a polynomial, right? A variable minus x. It's a small polynomial, but it's technically a polynomial. Okay, so take the commitment to the polynomial, divide it by this other polynomial, and that's going to result in something that is also a polynomial called q. All right. And I'll give you a commitment to this polynomial q. And if it's true that this divided by this equals this, then this has to be a root. Otherwise, this would not be a polynomial. Okay. If this isn't a root, then this would be a rational function, and then q is not going to be a polynomial itself. All right. So what I'm going to do is I'm going to do that mechanically. I'm going to take my polynomial. I'm going to divide it by this, figure out what the q value is. Okay. And if you want to think about it in terms of what we're seeing here on the screen, it's just whatever the leftover roots are. So once we divide off this one root, then whatever's left over will be q here. All right. And I'm going to send that to the verifier. Okay. So here we have Alice as the prover, Bob is the verifier. So Alice sends a commitment to the original polynomial. Then Alice says, I'm asserting that x is a root. Bob doesn't know whether that's true or not. He doesn't know whether to believe that or not. So he says, well, give me proof that x is a root. And Alice says, okay, no problem. Here's a commitment to this polynomial q. Okay. This polynomial q, I'm telling you it's the original polynomial p divided by this polynomial with this x value that I'm claiming. So the x value is a root. I'm putting into this bottom value. I'm dividing it off, and I'm going to prove to you that that is a proper q. Okay. And notice that this statement, you can just rearrange it into multiplication. Instead of it being division, you can move this over to the other side of the equation. And so it's equivalently, I'm saying that this multiplied by q will give you this polynomial p. Okay. Now, Alice isn't giving the value p itself. She's not giving the value of q itself. Okay. What she's giving is a commitment to p and a commitment to q. So what Bob has is he has a commitment to this p value, right? Which is just g to the power of p tau. That's what that commitment value is. She's giving a commitment to the polynomial q, which would be g to the q tau. Okay, so the commitment to polynomial q is g to the q tau. Okay. And these are secret, perhaps. So no one knows what p and q are. Okay. But the verifier Bob does know everything about this equation. Okay, they know what x is because that's what I'm claiming. I'm claiming x is a root. So there's no secrets involved here. This x value is a public value. Okay. And you can think of this as a polynomial. Okay. So it's a polynomial minus x, where x is a value. So I'm just saying 17 is a root. So think of x. It's not x like the variable in a polynomial. In this case, x is an x coordinate. It's like 17 or something. It's the um, it's the value where it crosses the axis. So we'll say that it equals 17 here. Okay. So that's what I'm putting in for 17. So my little equation here is just 17 plus 1 is that. Okay. So that is a polynomial. Okay. So my first coefficient is 17. My second coefficient is 1. It's a degree 1 polynomial. All right. I can commit to this using KZG myself. Okay. What I'll do is I'll take g, raise it to the minus x, and then I'll take g, sorry, this should be a negative 17. And I'll take g to the tau and raise it to a 1 because my coefficient here is a 1. All right. Now I have a polynomial evaluated at tau, g to the polynomial at tau. Okay, so this equals g to this thing at tau. Okay, this, we call it poly here. So I'll just put poly here. All right. So now what I want to do is I want to check whether this equation holds or not. So, the prover came, so this was the original polynomial I received. This I can compute for myself. So I'm content with this. This is what the verifier is asserting happens if you divide the polynomial that you were given by this value. Okay. So they just say, I did this division, and when I did this division, I get this Q value, and here's a commitment to it. But they could just make up any Q value. You have no idea whether it's right or wrong. So what you need to do is you need to check whether this Q value is correct or not. So in order to check it, I want to check that this multiplied by this is the same as this. Okay. So how do I do it? Well, I can check a multiplication homomorphically using this pairing operation. Okay. So I'm going to check whether the commitment to P is the same as the commitment to V and the commitment to Q. V here is what I named this. I see it now, so I maybe just add this here. So I just to give it a name, I started calling it V. I'll put that as V. Okay. So and yeah, so this is a commitment to V here. All right. So I have G to the P tau, G to the tau minus X, and G to the Q tau. All right. And with the pairing, what I can do is I can move these exponents to the outside. So I get P to the tau out here, and then I get tau minus X times Q to the tau outside of it. So it's the multiplication of this exponent with this exponent. Okay. Now this can only be true if the exponents are true. Okay. So P of tau has to equal T of X minus Q tau. All right. And so if this check holds, that's the exact equation that we were trying to solve here. That's the check that we were trying to do. The only difference is that we filled in the square with tau. So what this proves actually is it just proves that this multiplication holds at the value of tau. It doesn't necessarily prove that it holds at all other points, but because of Schwartz-Zippel lemma, if it holds at tau with overwhelming probability, it's going to hold at all points along the polynomial itself. Okay, so by doing this third step where I send you, I have this value of Q, I send it to you as a commitment, and then you just check whether the pairing of the commitment to polynomial P with G is equal to the pairing of the commitment to the polynomial Q and the commitment to polynomial V, whether that pairing check holds. If that does hold, these two values are equal, then you're satisfied that this value X is a root. Okay, so this statement is correct. All right. And if the statement is incorrect, it's not actually a root, then something's going to break down with overwhelming probability. You won't be able to do this check. Okay, so I don't know if it was clearer this time. It's a lot to internalize. I know it took me a long time to sort of read this and understand it, but I'll pause if there's questions here. The good news too is also if you don't fully understand all of these little details, you can, after this lecture, you can basically treat it like a black box. Just assume that there's this box, I put a polynomial in, it commits to it. And once it's committed, I can open up random points on the polynomial. I can't tell you how it works on the inside. I just assume that it exists. Okay. Now, for an exam, there'll be some level of questions on how it works inside, but not all questions, right? So you'll be able to answer lots of questions of even stuff that we haven't talked about yet, even if you don't necessarily follow all the internal details of this. Okay, then the slight variation is, let's say I want to prove that a point xy is on my polynomial. Okay, so I have a polynomial and the point is xy. So it's no longer a root. It doesn't necessarily cross at y equals 0. It's just an arbitrary point. All right. So what do I do? What I do is I simply take the polynomial and I slide it down by y. Okay, y is the y value that I'm claiming is on my polynomial. And now that point, if xy is on this polynomial, when I slide it down by y, then x0 will also be on will be on the polynomial that's been slid down. Okay, so sliding a polynomial down is easy. I just subtract. I do subtraction. Okay, and so what I do is I send a commitment to P. I'm going to prove to you that XY is on P. And so what I'm going to do is I'm going to take P, I'm going to slide it down by Y, and I'm going to prove that X is a root on this new polynomial. And how do I prove that X is a root on a polynomial? Well, I follow this process exactly. Okay. And so if I just have a commitment to P, how do I slide down the polynomial by Y? Well, what I do is I take my original commitment to the polynomial, I multiply it by G to the minus Y. And so that's going to equal, so the commitment to the polynomial is G to the P tau. G to the minus Y will be this. And so that's going to give me G to the P tau minus Y. Okay. So that's how I slide the polynomial down. Or in other words, if I don't know P, I just have a commitment to P, can I get a commitment to P tilde where it's P that's been slidden down by Y? Okay. And so the answer is yes, I can. If I only have a commitment to P, I have no idea what P is itself. I can slide it down by Y using just a commitment to P simply by multiplying it by this. If I multiply it by this, then I get a commitment to P slid down by Y. Okay. And then what I'll do is I'll take this thing and I'll take the X value and I'll go back to this protocol. And now P tilde is this value and this X value is the X value. And then I just do the proof. Okay. So basically I slide it down and then I convert it into a proof of what the root is. And then I just do the proof of the root itself. Okay, so that's sort of the recap of this KZG stuff. I'll again, I don't know if there's any questions about it. Please unmute yourself or ask in chat, or if there's anything that's unclear. Okay. I don't see any problems with it. I'm not believing that it's perfectly clear just because people are too scared to ask a question. But again, try to understand this as best as you can. There'll be some questions on the exam about the internals of this, but if you just cannot wrap your head around it, it also is not the end of the world, because it it's something that we can sort of put a black box around and not really have to know how the internals work in order to actually use it in the zero knowledge system that we're trying to build, which is Plonk itself. Okay, this is a good sort of breaking point. Introducing Plonk itself will be a big thing. So I'm going to save that maybe for next lecture itself. So why don't we'll just sort of end the class early today, and then I'll see you all in person next week. And then we can actually start using, so we now have all the building blocks, and it's taking a long time to get here, and thank you for your patience. But then we can sort of put it all together and actually use it. Okay. All right. I'll see you all next week.
Thank you. Have a nice